So the problem is 95, 46, right? So, again, the algorithm is simple enough. 5 plus 6 is 11, so you enter the 1 here, and this 1, right? And here is not at 9 and 4, but 9 and 4 and 1. So it's 14. So again, you enter the algorithm asks that you enter the 1 here, and it's 4. And then you have another column here with nothing. Oh, by the way, yeah, I should have done it better. I said, you see the 1 here, and then you just 1, right? But it's really not that. You know what it really is, right? Yes. Now I remind you of this. The zeros are always in front, but we decided to omit them. But now, if you want to make it conceptually robust, you're adding 0 to 0 to 1. So there's no, you're not deviating. You're not doing anything extraordinary. You do exactly the routine thing. This one. Oh, wow. Now quickly, I mean, how do you explain this? Well, you can, now, I didn't say explicitly how, but you could have explained it in terms of so many bundles. That's fine. I'm comfortable with that. But it would be equally okay to say this is 95 plus 26 is equal to 9 times 10 plus 5 plus 4 plus 10 plus 6. Okay. And then, now by the way, you notice how much we're relying on commutative law of addition, the associative law of addition, which guarantee that I can add any two numbers any which way I want, right? And then I'm using distributive law, right? So don't forget that. So this is 9 plus 4. See, this is what I mean by conversation among adults. We're here doing this, and we know exactly what's going on. But you don't want to burden your first grader, second grader and say, that's associative law, or that's commutative law, or that's this. Just do it. For kids of that age, you don't want to bother them with things like that. Plus 5 to 6. Right? And then, of course, now at this point, it is exactly the column by column addition. But now you say this is 10 plus 1. This is 10 plus 3. Okay.
10 plus 4.
No, not yet. Not yet.
Oh, 10 plus 1 on this side still. Okay.
So now, you see, I suggest that you write as slowly as I do. Some of you, which is okay, your own writing, you just skip a few steps. But if you want to be a good teacher, you have to learn to do things slowly. Right? So you of course, it's repetitious and so on, but for them, it's much better than your repetition. So then it becomes, now here I definitely tell you I'm skipping a step, right? Because I'm putting it in, I'm using distributive law, so it's one extra, right? You forgot. Okay. And then the rest are let's finish. Yeah.
What do you think about instead of going from your second line where you have 9 plus 4 and
I should keep it that way.
you got it. Leave it as 9 plus 4
Yeah, I should
plus
keep
1
it
so it matches the algorithm perfectly.
I keep it that way. Thank you. That's a good idea. Yeah. That's much better.
Yeah.
That is exactly the second column. Now this corresponds to exactly the second column. The first column we already taken care of that. Here is 1 to 1. 1 and 1. So then I see that this is, now I finally can say 10 plus 4, right?
Yes.
And then the distributive law tells me it's 1 times 10 squared plus 4 times 10 times 1. And that's exactly what this is. Okay? Now, we have to take a break. Before taking a break, I want to make 2 comments about the addition algorithm. Now, to understand the most basic aspects of the addition algorithm, illustrating with adding 2 numbers is good enough. On the other hand, you should not let that completely dominate your thinking and say, well, when I add numbers, all I ever do is, well, carry by 1 extra, that's it. That's not true. You can add what? Not just 2 numbers, any number you want. For example, right? All right, put this way. 7 plus 5, 29 plus 79 plus 67. What if I do that? Can I do it? Of course I can. Of course I want to do it on purpose. Now let's do it. So that's 5. You do exactly the same thing. Line them up. You still do column by column addition. And of course, you remember, right? You're always adding 3-digit numbers. Except that some of them are fake, 2-digit, but that's fine. All right, now let's see. So now, this is 16, 25, 33, right? 32. 32. And that's what I want to show you. The carry is not always 1. When you add 2-digit numbers, the carrying is always 1, at most. If there's any carry, it's 1, because you add 2 single-digit numbers, how big can you get? It's between 10 and 12, between 1 and 10. But it doesn't have to be. It's 3. Yeah. And the next one is bigger. Right? So 10, 23, 26. No, not bigger, but at least 6. And then it's 7. 5. Now, I don't think you want to see me write down that explanation. No. It's more of the same. You've seen one, you've seen them all. Right? Right, that's the first comment. The second comment runs against the grain. Now, what we have done? We're emphasizing face value. Everything depends on having the fact that 9 and 4 belong to one category, and 4, 5, and 6 to another, and so on, right? Oh, incidentally, that's why I couldn't find it in my book, I know it's there, but this morning, Stephen and Winnie made you do this problem about goldfish and silverfish.
Yeah.
Huh?
Angelfish.
Angelfish. Do you know why that problem was put up? Did it? I asked you. Remember, I said, does it remind you of anything? Remember? Okay, now I ask you the same question. Do you remember what you did this morning? Yeah. Did it remind you of anything? That's exactly the idea behind the addition algorithm. I don't know what number was. Let's say 5 goldfish and 7 silverfish.
4 goldfish.
4 goldfish
One
and
of
7
them,
angels.
right? Each one has a cost. You want to find the total cost. What did you do? You didn't just say, here is a goldfish for 40 cents. Oh, here is an angelfish 70. Oh, there's another angelfish 70. Oh, that and a 40. You didn't do that. What do you do? Lump all the goldfish together. Lump all the angelfish together. But that's what we did. That's what we're doing. I didn't want to say, oh, add the 9 to 6. Nothing like that. The 5 and 6 are the goldfish. The 9 and the 5 are the angelfish. I first lump together the goldfish, lump together the silverfish, the angelfish. That's what we did. That's exact. This is why they gave you this problem. See? So when you think like that, you see, it's entirely natural. You should convince your students of this fact, that they would have done the same were they in that position. Right? You want to increase learning, that's what you should all the time. Make them believe that they would have done the same. Right? So that's place value. You add two numbers of the same place value. Got that? Now I'm going to say, the next thing I'm going to say is completely contrary to what I just said. The whole point of the addition algorithm is that you ignore place value altogether. Understand what it says?
Yes.
Well,
Is it single digit?
it's
All
single
single
digit
digit.
operation all the way through. The best way to illustrate it is, so for example, consider two 57 1. Okay? 1, 1, 5, or 1 from 5, 2, 3, 3. Look at these two additions. You know how to add, of course, right? 8, 7, 3. 3, 8, 8, 9. And you know why I gave you these two examples, right?
No regrouping.
Not that, but
Oh, 3.
here is 5 and 3, right? What are they here? 500, 300. Do you care?
No.
That is the whole point. That is the whole point of having an algorithm that is completely position independent. That is the power of the method. Because if the computer has to worry about not adding 500 to 300, so I must do something one way. Here is only 5 to 3, I do it another way, your computer would go crazy. And that's what simplifies the computation. You don't care what it is, just do it. And that is what you should impress on your children. That, of course, after you have explained to them why the algorithm works. After that, they can learn the higher truth, which is what? Yes, it depends. The real reason is that we have this firm foundation of place value. But once you know that much, you can ignore it. That's why it's powerful. And that's what educators want you not to know. That is anti-mathematical. Mathematics is what it is. So the talk in the math was about in the debate on whether we should teach standard algorithm. They said the standard algorithm makes you forget place value. Well, yes, of course it should. That's what it's supposed to do. That's exactly what it's supposed to do. Right? Of course, provided you know why you're doing it. But when you don't know mathematics, you just say, oh, that's that. But you see why it's good, right?
Yeah.
Simple. Simplicity. You have to pay for everything. If it's simple, you pay with a high price. What's the high price? The high price is a firm understanding of place value. And you cannot ignore mathematics and just say, oh, the superficial features look bad. That's not it. That's not it. That's the whole essence of the algorithm. Okay, let's take a break and then I'll see how far I can go with the subtraction algorithm.